Hello. Today we're going through the next lesson of electrical circuits where we're going to look at the specified practical that's required to investigate what's going on with components and work out their current and voltage. So I'm going to talk you through the steps required for this practical and what you would need to do during an experimental exercise as well. And then we're going to look at the graphs and see what we can get from those graphs for different components. Starting with the simple equipment, I've taken a circuit diagram from a past paper question. It's not a complete circuit, but you should be able to see we have the battery at the top, and then as we work our way around clockwise, we have a bulb connected to a variable resistor and back to the battery or the power supply. So in the picture I've represented this, it's a bit difficult to photograph, but you've got the power supply at the back, and then I've used red cables to build this particular part of the circuit. Okay, so it's leading round to the bulb, the variable resistor, which we looked at in a previous lesson, and then back to the power supply. And it's working on that idea that we talked about before, that the variable resistor will change its resistance, and the more resistance it has, the more voltage it will take up. So if we move on to the next slide, you can see as the slider moves across, that lowers the resistance of the variable resistor, and therefore more currents flow in. The variable resistor is using less of the voltage, so more of the voltage goes to the bulb and the bulb gets brighter. Move that slider along again, bulb gets even brighter again. But that's not enough to conduct the actual experiment. We need to be able to collect data, and for that we need meters. Our first one is a voltmeter, and a voltmeter would need to be connected around the bulb because it's the bulb that we're actually interested in. And that would be the first mark on a typical question, to actually add the meters required to the circuit diagram provided. So you'd need to add a voltmeter in parallel around the bulb, and that would take the voltage measurements for the bulb. We'd also require an ammeter, and I've connected the ammeter between the variable resistor and the power supply. But as we talked about in a previous lesson, the ammeter doesn't need to go in any particular point as long as it is somewhere in the main loop. So anywhere in this main loop would be absolutely fine. Okay, so you'd get a mark for adding a voltmeter, a mark for adding an ammeter anywhere on that main loop. So it's a fairly simple method for this. You wouldn't need to explain how to set up the circuit because that would be given by the diagram. And all we need to do is set that variable resistor to a maximum. And the reason we do that is we want the variable resistor to take most of the voltage so that when we first switch it on, there's not too much voltage from the bulb and we potentially damage the bulb. We then switch on a circuit, which is a slight downside to the circuit diagram from the past paper in that it doesn't have a switch, but the power supply will, or we can just take a cable out in order to make a gap in the circuit. Once it's switched on, we take a voltage reading from the voltmeter, a current reading from the ammeter, and write those down, switch it off, alter the variable resistor a little bit, and then switch it back on to get more readings. And we keep moving the slider on the variable resistor until we've got at least 5 pairs of readings. Now, ideally, we would want that to be from 1 volt to 2 volt to 3 volt and so on, but it would depend on the equipment provided. Next, we're going to look at the process of collecting the results. So I've compressed the circuit a little bit to fit on screen, but on the right-hand side, we have the voltmeter connected by these black cables are either side of the bulb. And on the left-hand side, we have the ammeter in the main loop with the bulb, power supply, and variable resistor. When we're constructing our results table, it'd be voltage first because that's what we're controlling. That's our independent variable for which we're using a variable resistor. And we're measuring the current, so that's our dependent variable. And I've set all of the readings to be whole amounts of voltages, which is a tricky process, but it is possible. Obviously, if you're under pressure in an exam condition, you would try and get as near as possible, as reasonably near as possible to collect those results. So you can see, obviously, if there was no voltage being applied, no current will flow. And then when we've got 1 voltage, we end up with 0.34, 0.58 for 2 volts, 0.75 for 3 volts, and so on. I'm not going to write them all down because obviously that'll take longer. What I did do was include a couple of slides at the end to illustrate what I mean about being as near as possible in exam conditions. So if this was your practical exam, you wouldn't spend forever trying to get it dead on 11 volts. So I stopped here at 10.99, and that would be a reasonable point to stop, but you would still record the value they wanted. So I would still write down 11 volts in my table. Okay, and just to show that I wasn't just slacking off, I did actually get it to 11 volts as well, but it took a little while because the higher the voltage, the more sensitive the equipment becomes to change. Here are the results presented in full as if you were carrying this out in a practical exam or for a written exam. When it comes to presenting these results for a light bulb, this is the graph that your results should produce. Obviously, experimental data might not be quite the smooth curve, but if it's data given in an exam, they would have to give you data that produces the graph that they actually want if you plot it correctly. The negative region just indicates exactly the same behavior if the current is flowing in the other direction. So light bulbs function irrelevant of which way round you connect them, and torches should work if you turn batteries around, if there was no other devices in there to stop that happening, like a diode. But we're only really interested in the positive region of the graph. Okay, so we have current up the side, or I, and V along the bottom, V being our independent variable because we were altering that with a variable resistor. And you see we get this gradually fading curve, so it starts a lot steeper than it ends. And that's an important feature, that it starts to flatten out. And the reason for that is that we can apply Ohm's law to this, our relationship for resistance, which is that the resistance is the voltage over the current. But for any graph, the gradient, how steep it is the y-axis, or a feature of the y-axis, divided by a feature of the x-axis. So that is I over V, which is the inverse, the opposite of Ohm's law. And therefore the gradient is 1 over resistance. It is this situation flipped up the other way. All we're doing is adding a divide by 1 and then turning both those fractions up the other way. Now that means that when the graph is steep, we have low resistance. And when it gets flatter, we get higher resistance. So when we apply a small voltage to a bulb, that will allow a certain amount of current to flow, but the resistance is quite low, so it's not bright. There's not enough resistance there to generate the heat to make the element glow enough for the gases to start glowing. But if we apply a much higher voltage, the voltage may have gone up 5-10 times, but the current will not have increased by the same amount due to that curve. So now we're getting a much higher resistance, and therefore we're producing a lot more heat, is making the element a lot hotter, and the gases within the bulb will start to glow as they should. So bulbs only function at the top of this curve, where the resistance starts to increase. Looking now at identical experiments but using other components, we could also carry this process out with a fixed or ohmic resistor, like we looked at in an earlier lesson. And because it's got a fixed resistance, that resistance won't alter irrelevant of the voltage and the current being applied, and therefore the gradient shouldn't either. Right? So the gradient will still be 1 over the resistance. So if the resistance is 100, the gradient will always be 1 over 100. And that shouldn't alter irrelevant to the voltage, and that's what gives us a straight line. Again, the negative region indicates that this would happen if you turned any of the components around the power supply or turned the resistor around as well. Exactly the same would happen if the current was flowing in the other direction. Looking at that positive region, it is important to appreciate that there's a relationship between how that resistance changes. So it's not just that if the resistance drops, the graph gets steeper. It's actually proportional. So if we was to double the resistance, we would actually halve the gradient. So if you look at the line for the 100 ohm resistor, when we were measuring the gradient, we would use this triangle, which has a height of, keeping it a height of 5 squares. Okay, 4 squares, taking us up to 40. If we then halve that resistance, we would then calculate using a different triangle. So halving that resistance to 50, which would then give us this triangle for the gradient. Now the base is exactly the same, so x hasn't altered, but the y-axis now is 8 squares high, or reading across takes us to 80. Okay, so from 100 ohms to 50, the resistance halves and therefore the gradient doubles. This line is twice as steep as this line. Okay, and it's important to be aware of that relationship when you're looking at these, because they might ask you to add a second line on a graph for a resistor that has a higher or lower resistance than the one they were originally talking about. Final component we're going to look at doesn't crop up much in exams anymore, but it is one you need to be aware of. It's a diode. And they like this. Obviously, it'd be exactly the same for an LED as well, a light emitting diode. But we have a flat line in the negative region. Now, that's not the complete story. You do have a breakdown point. You can force diodes to function if you apply a high enough voltage to it. But for GCSE, as far as we're concerned, if the current's flowing in the opposite direction, no current flows. So it should be flat in the negative region. We also get this steep upward curve just past 0, which occurs around about 0.6 volts. So key to a diode is it starts to function at low voltage, which is why we can make things like TV remotes work off very small loads, very low voltage batteries. And once we exceed that 0.6 volts, the graph gets very steep very quickly. This doesn't really reflect it as it should. It goes up exponentially and gets extremely steep very quickly. So it drops to almost no resistance when you have a very small current applied. And that means obviously all the energy from the device is going where it was meant to be going rather than producing heat. So LEDs and diodes are very effective, very efficient devices in terms of switching on at low voltages and producing very little wasted heat when they are functioning. This final slide is more for exam-based context, where they can ask you to compare what's happening to more than one component on a single graph. So you can see we've plotted a solid black line for a light bulb and a dotted red line for a resistor. The key point here is where the two lines overlap. Now at this point they would have identical voltage and identical current, and therefore they would produce exactly the same amount of power, and they would also have the same resistance. Okay, so that is a key thing to know. Where the lines overlap, they are behaving identically. The other thing to realize is that the relationships that are seen below that point are reversed when we move past that point. So below that point, one component will have a higher resistance than the other, and above that point, it will have a lower resistance than the other. And the same is also true for power. The relationship will be reversed. Now, if you're ever stuck on working out which one's which, you can just run through a quick calculation. So if we take 3 volts and work out the resistance for both. So 3 volts up to the line and across. So for the light bulb, the current is 0.5 amps. So the resistance for the bulb will be voltage over current, 3 volts over 0.5, giving a resistance of 6 ohms. We then do exactly the same process for the resistor, up to the dotted line and across, gives a current of 0.4. So the resistance for the resistor is again voltage over current, 3 volts divided by 0.4 amps will give a resistance of 7.5 ohms. Okay, so below the line, below that point where they cross, the resistor has a higher resistance than the bulb. When they cross, they will both have 7.5 ohms. And then as they move past that point, the resistor still has 7.5 ohms of resistance, but the bulb will now have a higher resistance. And it's important to understand what we can interpret from those graphs in exam conditions. So to recap what we've covered, you should now have an understanding of the steps you need to go through to investigate the voltage and current characteristics of different components. It's all the same process. All you would do for a different component is change that bulb and follow the same steps. But obviously that would produce different results in a different graph. You should be able to recognize sketches of those three graphs for the main three components that you can be asked about. And you should have an idea of how to interpret them as well, in terms of the gradient being the reverse of the resistance. The steeper it is, the lower the resistance. The flatter it is, the greater the resistance. So I've put together a quiz for you of some past paper questions and some questions about the steps required. So if you give that a go, see how you get on, and if you've got any questions, let me know. Thanks.